if you're riding a car in a tunnel, when you roll down your window, you will hear the boom, boom, the booming sound. You actually feel the pressure in your ears. That's low frequency, about 100 to 300 hertz. Tunnel, the noise has nowhere to go, so noise has to bounce back and forth. Also, in living environment, in a theater, in a concert hall, we want to prevent the sound back and forth between the walls. Long-term exposure to the low-frequency noise, you get trouble sleeping and cause stresses. So that's why many cities have put these regulations to prevent the low-frequency noise in urban areas. Have you ever noticed in a theater, the walls often have panels? They're there to absorb sound. So the current solution normally pretty bulky, and each one of them only works for a particular frequency. Currently, the main solution is to use the mechanism so-called Helmholtz resonator, which was discovered by scientist Helmholtz about 160 years ago. This structure works well for a given narrow frequency range. But the frequency spectrum, for example, the traffic noise or the concert hall, is pretty broad. Therefore, they have to use many of them. That causes the structure very bulky and complicated. So our invention is you replace this rigid material with a soft, flexible material, reduce noise and absorb sound in a much broader range. But it all happened a bit of accident. So one day, my student Yanlin, he saw other lab mates are all using a soft material, working on robotics. How about we also try to use some soft materials on the acoustic study? And the results are quite a surprise, which cannot be explained by the traditional Helmholtz resonator. It's very different. This soft material we use particularly is very similar to chewing gum. This measurement actually tells us what's the mechanism why the soft material can absorb low frequency sound. The sound pressure will make the soft material vibrate. When you walk in a room, when you speak or you clap, you hear a clear echo. When you put in these panels with our sound absorption soft material, so now you will already notice my sound does not echo. There's no echo sound. That's the demonstration I want to show to the general audience to let them know how sound absorption can impact their daily life. So initially, it is more engineering problem because we try to optimize structure. And gradually, we found this is a more scientific problem. From experiments to simulation to analytical understanding to how to present a very scientific way. That is also a good way to train students. Want to see how far we can push this methodology. Can we make the material be adaptive in real time? Can we absorb the sound depending on a different environment? Make it real useful to larger structures, tunnels, or concrete. That will be a huge pride for us to make this fundamental research useful to normal people's daily life.